The term black box is used to describe any AI system whose input and operations are not visible to humans. Essentially, the system works in secret, with data flowing in and a decision coming out, without anyone knowing what happened in the middle, since the operations are hidden in the so-called black box. A machine learning model doesn't simply follow instructions provided by a programmer. It makes predictions and recommendations based on patterns detected in data. These models are created by someone who provided the data, selected the algorithms, and supervised the learning. By design, a machine learning model improves itself with practice, and it may evolve past the understanding of the person who created it. There is a potential for harm to individuals. Many AI systems are used to profile people or to perform other tasks that may have a direct impact on people's lives. For example, there have been instances of resume sorting algorithms that might exclude some people from consideration for a role because they don't fit an established pattern of candidates for that role, even if they themselves possess the necessary qualifications. Algorithms are often used for extrajudicial judgments, such as credit scoring or keeping track of people barred from nightclubs, to create a personality profile from one's online presence, or even for criminal sentencing or the pricing of bail bonds. Such decisions are very difficult to challenge and present a tremendous risk to liberty and access to justice. This is particularly the case as the awareness that one is being judged is typically poor, and there is no recourse necessarily to see what one's score is, to challenge a judgment, or even to know who is responsible for having made that assertion about one. People have a right to know how decisions about them are being made in a way that they can understand. Worse still, even the creators of these algorithms often may have no idea how or on what basis a decision has been made. Deep learning systems can work really well, but they can also fail in puzzling ways. They are non-deterministic by nature. Due to the inherent randomness in the statistical models, the same input may not necessarily give the same output each time. Also, as they are dependent upon data, any update to the data, as well as any update to the model, can change the function or the results generated. This makes these technologies difficult to rely on, as they cannot be trusted to always return the same value. Furthermore, due to the nature of deep learning, it can be very challenging to understand which specific piece of data within a dataset contributes towards an output. One might notice that a prediction has changed due to an updated model or dataset. But why? Tracing the specific data points that are influencing something within a deep learning dataset is challenging due to the complexity and depth of the models. The difficulty in understanding is described as a black box problem. Input goes in one end and output emerges, but the processes between are shrouded in mystery. This can also make it more challenging to debug biases, as biases may lurk within the data, model, or both. Which is primarily at fault? This is especially the case with federated learning systems, whereby data may pass between multiple data sources and models, perhaps with uncertain provenance also. Concerns about black box issues have led to legislation that requires fairness and transparency within algorithmic systems. For example, data protection regulations provide users the right to demand access to all data held about them. Newer legislation is beginning to mandate the provision of transparent and explicable readouts of algorithmic decision-making processes and the data that those are predicated upon also. One can start by probing the system in a step-by-step methodical manner. By adding or removing data to a dataset, one piece at a time, one may discern which elements might be contributing to a certain output. Maintaining consistent versioning of algorithms and datasets can help with understanding at what point a problem may have arisen and to provide clues as to the root cause of an issue. However, commonly an output might be built from a combination of variables rather than just one on its own. Making sense of so many variables is often much more difficult. Therefore, this process might not be sufficient or practicable to shed enough light on the system's inner workings. It may be possible to apply one form of machine learning model to help understand another, however. For example, CNN-Viz aims to create a visual representation of how a convolutional neural network generates impressions about the objects it perceives. It can analyze the respective flows of saliency as they pass from one layer to another, and thereby trace back the data points that contribute the most to a certain input being tagged in a certain way. Visual analytics systems can help developers and auditors to better understand the relation between various elements. Sometimes a picture speaks 1,000 words, and a visual representation provides a holistic and intuitive picture of the network's inner workings. CNN-Viz is oriented towards understanding convolutional neural networks, which usually, but not always, are applied to making sense of visual information. Other tools may help with other kinds of machine learning systems. SHAP, Shapley Additive Explanations, apply game theory to creating an explanation of a machine learning model. Similarly to CNN-Viz, it can map the dependencies of a specific output to elements above it, although the output is statistical rather than visual. Other techniques, such as radioactive data, aim to highlight data, similarly to how ingesting a barium meal can help make soft tissue show up on an X-ray. Radioactive data makes data flows significantly more trackable by adding a small smudge or perturbation to data. That isn't significant enough to meaningfully alter the function of the data, but it is enough to track it as it flows through a model or especially between federated systems. These radioactive features are difficult to detect if one doesn't know what to look for, and so they may also be applied to quietly watermark data to track unwarranted usage of it. Therefore, whilst the black box problem is a persistent challenge for machine learning engineers, particularly those attempting to uphold ethical integrity, we do have some tools that we can use to make these issues more tractable.